This lesson, we're going to cover the first of a three-part series looking at our oceans. Today we're going to discuss general oceanography, and then we're going to take a look at the ocean floor. The whole world's oceans are interconnected. You can see from the southern hemisphere, the ocean hemisphere, because most of the land resides actually north of the equator. Around the continent of Antarctica, all of the oceans are connected. There is a current that circumnavigates the globe there. The major oceans are separated into basins, though, where the largest being the Pacific, the second largest and still growing, the Atlantic. You have the Indian Ocean. You have the Arctic Ocean, which is the shallowest and mostly under ice. And then you have the Southern Ocean, which does have some plate tectonics going on in it as well. So approximately 70% of the Earth is covered with ocean. The average depth is more than 3.7 kilometers or 12,000 feet. The average water temperature is right around 4 degrees Celsius. That is water's maximum density. So below the sunlit layer and the transition zone, you are looking at a fairly stable, dark, cold environment. And the average salinity is 35 ppt, which is parts per thousand, or 3.5%. So looking at the distribution of water, we talked about hydrology last lesson. You can see ice caps and glaciers, which is not potable. And then below that, what is usable is a very small fraction of the water we find on Earth. Most of our water is salt water. The largest is the Pacific Ocean. The Marianas Trench is the deepest portion of the Earth's crust. It's also called the Challenger Deep because one of the expeditions, called the Challenger Expedition, discovered it using sonar. The Atlantic Ocean Basin is actively spreading. Its deepest point occurs in the Puerto Rican Trench, which is over 8.6 kilometers deep. The Indian Ocean, average depth 3.9 kilometers, and its deepest point occurs in the Java Trench. The Arctic is the small region north, mostly covered with ice. And the Southern Ocean Basin does have the Sandwich Trench, which gets to over 7 kilometers deep. So the average depth of the ocean is 3.7 kilometers, yet the average height of land is only 0.02 kilometers or 245 meters. This is a very telling pie chart. The ocean, which makes up 70.8% of Earth's surface, covers 11.4% of the continents. The continents extend out into the ocean, so as glaciers recede, grow, recede, it's exposed, covered, exposed. Currently, continental shelves make up 11.4% of Earth's crust. They're continental, they're granitic, shallow, so parts of the continents are currently underwater at present. So when we look at the ocean floor topography, you can break them up into the continental margins because it's distinctly different granitic rocks, and then the ocean basin or the abyss, which is basaltic rocks. The shelf drops off from the granitic shelf to the deep ocean abyss, basaltic, that's called the slope. The shelf break is where it ends, And then continental rises are the buildup of sediments that have eroded from the shelf to the ocean deep. Looking at this image, this is exaggerated, so you can see the extreme change from the slope and then the sediments sitting on the deep ocean floor. And then the continental margin is where that sediment ends and all you have is deep ocean floor. You have two major types of continental margins. The active, where that's a subduction zone. You can see the Pacific boundary where the coastal uplift forming mountains, very narrow shelf, deep sea trench, those are the deepest areas. And then the passive margin, you can see on the right, the Atlantic side, very wide shelf, gentle slope, and then your plate boundaries far out to sea. So you have the active margin, which we refer to as the Pacific type, and then you have the passive margin, which we refer to as the Atlantic type margin. The shelves are the steep drop-off. Now, if you look at the graph on the right, you can see how sea level fluctuates over time. At point C, where we are today, we're at a very high sea level. That means our glaciers are very small. It's not the highest in the recent history, but it's pretty darn close. So much of our continent is under water at this time. Here's a 3D image showing the passive margin with the wide shelf, the steep slope, and then the abyssal floor. Old riverbeds and valleys form submarine canyons. They are not deep sea trenches, which are formed by subduction plate tectonics, so they're shallower, and they run perpendicular to shore, as that would be the direction of the river. There are depositional environments, usually at the bottom, deep sea fans, huge continental rises. Here's another image depicting the Hudson River Valley Canyon. Now our deep ocean basins, which are basaltic, contain the ridges with vents, hills and plains, seamounts and guyots, and then we have our areas of subduction, the trenches and the archipelagos or island arcs. This shows all of the spreading deep sea trenches. The numbers are given speed that it's spreading, speed. So you have 1.5 centimeters spreading or 15.7, very fast 15.7, very slow 1.5. But if you add these changes up for millions of years, they all become quite vast. The green areas on this map, incidentally, are areas where the plates are being pushed together. Those are subduction areas. Take a look at the Caribbean Sea. You can see that green loop. There's where the Puerto Rican Trench would be. You can see there's the archipelago, the Caribbean islands. So that is an active center. You can see the Sandwich Trench in the Southern Ocean, kind of off the coast of South America. So those are all look at the Himalayas where India is. Those are the highest landmass. So this is very telling as to our deep sea topography and our land topography. Hydrothermal vents are also called black smokers because the sulfur bubbles out. It's not really smoke. Organisms take advantage of this through a process known as chemosynthesis. So very primitive ecosystems are jammed in the ocean deep. No sunlight, no photosynthesis. Chemosynthesis drives them. The abyssal plains are the largest feature of your typical ocean floor. They are wide expanses of basaltic ocean floor. Extinct volcanoes can be rounded called seamounts or flat-topped called guyouts. They generally are areas where life aggregates because they're shallower, so there's sunlight and a little warmer temperature available. Also, upwelling can occur on them because the deep sea currents get forced up. Upwelling is a current that comes from the bottom, and they generally are nutrient and oxygen rich. So upwelling leads to increased biodiversity. So these seamounts and guyouts are like oases of life in our deeper oceans. Trenches are areas where subduction occurs. They are the deepest, and they're very prone to tsunamis, very prone to earthquakes and volcanism. Now, our ocean sediments are the accumulation on the ocean floor, much like soil is the accumulation on land. You can have terragenous from the land, so the continental shelves and those continental rises are more terragenous from the land. The deep ocean doesn't get that land influence as much. It could be clay because clay is so small, so that would be a minor land influence. Or they're also called biogenous because they're from the sinking of biological particles. So terragenous is land-based, biogenous is biological. Hydrogenous precipitates directly from the seawater, generally due to temperature change, and cosmogenous comes from space. Glaciers, erosion lead to terragenous sediments. They're the thickest, most by mass, but they don't cover the greatest area. They are the most massive, though. We actually have oil deposits come from both terragenous, that's sedimentation, mixed with biogenous, that's where the actual fossil fuel comes from, biogenous sediments. So these sediments we use for fossil fuels. Terragenous sediments, shallow warm seas build up biologics covered with terragenous sediments, and that's where you have good oil deposits. There's biogenous sediments, like we said. You can have the calcareous or calcium-based shells, the siliceous, and even phosphorus-based life. The foraminifera shells are just one of the plankton that contribute. Hydrogenous comes from the precipitation, generally due to temperature. The most common, or one of the more famous, are the manganese nodules of the deep. It's a metal that is precipitated out. We also can find some fossil fuels precipitate out called hydrates. And cosmogenous come from space. Notice how polished they are from flying through the atmosphere and being superheated. The distribution of marine sediments, like I say, the blue represents biogenous, as does the green. So they're thin layer, but it covers the most area. The abyssal sediments and the terragenous sediments are thicker, cover a little less area. I mentioned oils, natural gases, fossil fuel comes from sedimentation. The petroleum and natural gas is laid down, deposited, and then covered with terragenous, like sand and silt, and over the years it distills out and becomes oil and gas. I mentioned the hydrates, like methylene hydrate, which is a precipitate that the deep ocean can give due to temperature and pressure. Of course, we also mine the ocean for sand and gravel and even limestone. Gypsum, we have gypsum mined here in Florida from evaporites. We use that in the plaster. So gypsum is another important mineral that we get from oceanic influence. Of course, salts. Now, pulling salt from water takes a lot of energy, so we generally mine salt that is left from ancient oceans. And we mentioned the manganese nodules. They are not economically feasible at this time because we don't have enough use for them, but we do know that we have large stores of manganese. We also pull a lot of food from the ocean, so that's the biological resources.